By now, you should be able to see my screen. Am I correct? Is it there?
Yes.
Yes. All right. Good. All right. So the materials here is going to be concrete as a material, and then the strands or wires or rebars. Sometimes we have this bars. You can call it also rebars that we use for pre-stressing, like duodeck bars, for example. First, we're going to be talking about the concrete. You understand that you're going to be having here higher strength properties, generally speaking. If, like according to the previous example that we have discussed, we're going here to 270 KSI for the strength of the rebars. So we're not talking about 60 or 90 or 100. We're really working here with high strength materials. So you need also to bring to the picture here really strong concrete. You're not going to go here with 2500 PSI. Maybe you can go with 2500 if you're just doing precast. Precast was conventional rebars. But once you start here to bring the pre-stressing into the picture, you need to go to higher strengths. The standard that usually we see for pre-stress is going to be starting at 5,000 and maybe 6,000, maybe 7,000 and more. When it comes to the ACI code, you understand the ACI code doesn't have a limit on the concrete strength nowadays. But the typical is going to be between 2,500 to 6,000. If you go here again, 2,500, it's going to be mostly for precast, non-pre-stressed, maybe all the way to 4,000. If you like to go with high strengths, concrete, for pre-stress, you're going to be starting at 5,000, maybe 6,000, maybe 7,000. Once you go above 6,000, we're going to call it here high performance concrete. So just 6,000 is going to be okay. We just call it reinforced concrete or pre-stressed concrete. Once you go above 6,000, usually we start to call it here high performance concrete. And we'll keep in mind the same 2-unit weight that we use here for normal weight concrete and lightweight concrete. Lightweight concrete also is used in pre-stressed concrete. We use it a lot, especially when it comes to the double T system. And of course, you'll understand that the reason that we want this because we'd like to reduce the weight of the structure. Weight of the structure is going to be a big element, big factor here because the span of the double T usually ranges from 40 feet to 60 feet. So just imagine that you don't have any columns. And then at the end of this double T, you're going to have a line of beams, columns, and also you're going to have the lateral system. Most likely it's going to be either shear walls or reinforced concrete, pre-stressed or non-pre-stressed moment rings. Seismic, as you know, is going to be related to the weight of the structure. When you have bigger weight or higher weight, seismic force is going to be large, and you're going to be in trouble just to make it work. So you better try to reduce the weight of the structure as much as you can in the main elements. So in a reinforced concrete, pre-stressed parking structure, you'd go with the double T's to be lightweight, and the columns most likely are going to be going here with normal weight. So it is not necessarily that all the members can be made out of the same concrete in terms of normal weight or lightweight, but you can pick and choose. Beams, usually we do it out of normal weight. Columns can be normal weight. Double T is the thing that takes a big volume. We try to make it as lightweight. And we understand the reason. Our target at the end is to have lighter structure. This is a copy and paste from the ACI code from the 318/2014. This gave you the code that we work with. And as you see here, for the application, it says here, minimum concrete strength to be used in conventional concrete design and pre-stressed concrete design is going to be 2,500 PSI. And for the maximum, there is no limit. In the past, we used to have a limit. It used to say strength is going to be a maximum of this much. Otherwise, it is not covered in this code. So the question is, in the past, when the maximum was 6,000 PSI, what would you do if you like to use 12,000 PSI concrete? The material was there and is used in buildings, but it was not in the code, in the ACI code. In that case, we used to use an ICC evaluation research report that tells you how to design with high strength concrete. That was very famous. If you like to go to higher strength concrete, like 12,000, 14,000, you have an ICC research report, which is kind of extension to the code, if you like to call it this way. So there is a way around this by going to an ICC report. Now you don't need it because this ICC report is not going to be valid. You don't really need it because the code already starts to recognize the fact that there is no maximum for the concrete strength. You can just use any value and use these equations. We are not going to be doing here seismic moment rates. We are not going to be doing structural walls or pre-stress walls. So this section here for the lightweight concrete and the normal weight concrete applies for seismic. So this section here, I'm going to put the box. I'm going to say this is going to be for seismic. So this one is the one that we really care about. You have a minimum of 2,500 conventional concrete, and there is no max. This is very good. Now, the modulus elasticity for concrete. In the ACI code itself, it gives an equation. And it tells you here that E sub C, which means the modulus elasticity, according to this code section, is going to be equal to the unit weight. This is like gamma C, if you like, to the power of 1.5 times 33 square root of F prime C, and this is going to be in PSI. WC here is going to be ranging from 90 to 160. Once you go beyond this limit, you cannot really use this equation. This is what they're telling you. So try to keep unit weight of the concrete within this value. The very standard unit weight that we use when it comes to this equation is going to be 145 pounds per cubic foot. And if you plug it in this equation, you're going to end up with 55,000 square root of F prime C. This is going to be the common equation that you use in concrete design and concrete analysis. And in this case, the value of E sub C is going to be in PSI. If you like to do it in KSI, use F prime C to be in PSI and just say 57 multiplied by. So let me point at this. The F prime C value is going to be always in PSI, right? But if you want your EC to be in KSI, just take this value, the whole thing, divide here by 1,000. I'm going to say if you put this here in PSI, which you have to, you don't have a choice to use it in KSI, your E sub C also is going to be in PSI. Okay, good. One equation is going to be simple, and you have it in your notes, and you can use it whenever we need it. Any questions? Okay.
Is there a way to physically tell like high strength concrete from normal concrete? Because it's talking about stone aggregate size and the ingredients here on your slide. Can you tell by looking at it, or is it just something you have to know and design for?
No, there's as you know that there is a concrete mix design. Are you familiar with the concrete mix design?
I don't know it well, but I'm aware of it. Yeah.
Okay, yeah. So there's a way of doing concrete mix design, and generally speaking, people now don't invent or reinvent the wheel. You don't invent new mixes unless you have a new aggregate that you never used before in your life. But once you go to any like concrete supplier and ask them for any concrete strength, they're just gonna pull it from the shelf. I mean, they have big table or big library if you like. And in this big library, they have all the concrete mixes that you may think about with all different available aggregate to them. And they have it ready, and also they have it signed stamped by their engineer. So all what you need to do is just ask for it, and they'll give you the concrete mix design that's going to give you the strength. And not just that, they're going to give you also the mix trial, which means they're going to say, in the past, we have done it that many times, and here's the concrete test values. So you have also confirmation that this concrete mix is going to work and give you that strength. And here are the tests. And here's all the statistics about it.
I see that.
Yeah,
that's very, very interesting. Thank you. Very informative.
No problem, no problem. This is actually very common, and I can show you something here for quick if you hold it with me. Let's say in any project, right, that I'm working on any project, and all of a sudden I see here concrete mix design, right? For example, I have a project and my job as structural engineer is to specify the concrete strength. I'm not doing more than this, as you guys know. Yeah, second here. And I get you something here simple that all of you guys would be able to see it. Them avoiding anything here that has, let's say, the information. All right, this one, I'm just gonna be, I wanna show you guys this, is gonna be very interesting to you. But I'm just trying to cover here the project information, since it is not really mine. Okay. So usually, as you guys know, in the concrete submittal or in the concrete sheet, we put in general notes, we say, well, I'm looking for this many psi of concrete. And then what I ask him is to provide sign stamped concrete mix design to me. Here is one of the suppliers. So they send me this concrete mix design, which is something ready at the supplier place, at their office. And I was looking for 5,500 psi. The aggregate size gonna be 1 inch, right? And this gonna be good for pumping. So we know that they're gonna be pumping this concrete. Aggregate nominal size, which means the maximum, is gonna be 1 inch. And it's not air entrained. I didn't ask for air entrained. This is like one of the additives that they do. And they give you here the mixed properties. Look at all of this information. Amount of cement, total mass. And then what I do here, I sign a stamp that I have reviewed it. You see this with my stamp. And this is a stamp of the engineer who prepared the concrete mix. Some of the additives, like this WRDA 64, and this is gonna be good for workability. So I know that they're gonna be adding it. And they give you here all the aggregate that they're planning to use. They're gonna have this San Gabriel from Arundel, this give you the location, here's supply of the aggregate. They have all the information, specific gravity and the mass and the volume. So they give you this mix design, which they already have. And just, you know, this mix design, it has this mix ID. So they have huge library. It's full of all mixes that they have done in the past and test values. And look at this. Here's the grading. What you're looking here at is going to be the grading for the aggregate, right? Which needs to be also checked in the concrete mix design itself. And then they give you here the lab trial mix and the results. What happened when they tested before? Look, they have 3 tests that they have done in the past. And they did this on May 25th, 2020. They have 3 samples. And look at this results. The average at 28 days was 6980 psi. I was just looking for 5,500. And look at the trends they are able to get. In 7 days, that was the average. After 3 days, just tested 2, and the average was like 5,000 psi. So this is excellent, right? And they give you also more information. They tell you exactly the drying shrinkage. We're going to be going today through the shrinkage and creep. They give you the amount of shrinkage, right? So that you know if this is going to be acceptable to your design or not. And they give you here lots of other information. They give you all the chemical composition for the cement. I mean, you have the entire submittal here. So you don't really do any mix design these days because you have tons of this, unless all of a sudden we have new aggregate supplier. Let's say that you move to some place where one of these aggregate suppliers, they don't have enough aggregate anymore, and you need to move to another mountain from which they bring the new aggregate. In a case like this, you need to restart something new. And you have the methods, you have the templates ready. You just figure out the specific gravity, and then they have some design values. They came up now with specified strength, which let's say 5,500. They do some test samples, and they tell you, okay, we have done it, and here's gonna be the test values, and you should be good. And they put this in the submittal. So once I start the project, I ask for all submittals, and this is gonna be one of them. And once I receive it, I know that everything is good. We should be able to go ahead and use this. So as a structural engineer, you don't really get involved in the design because they have it already. You do it for tons of people. So why should you go ahead and do it yourself, right? Also, when they do the project, they give you some of the, this is, for example, that was submitted for pure compound. You know, when you do the concrete, hydration is going to happen. And if you are in dry weather, you will need to add water or moisture to the concrete surface. So this is the reason that we have this compound, pure compound, that you're going to be adding. You're going to spray it to the top of the concrete. And I need to review it and be sure that this is okay. There's no colorize in there. And it has an ICC research, evaluation research number, and I should be able to use it. So another thing that also I back check or review as the engineer record.
Professor?
Yes.
The concrete strength that you wanted was 5,500 at 28 days.
Yes.
The average strength was like almost 7,000 at 28 days. Was that okay?
Yeah.
Okay. So
this is gonna be okay because I'm looking for a stronger concrete, so it should be fine.
Okay. Is there like a range you don't want to go over?
No, this only happens when you have like a special testing, or you're doing like a research. If you are doing a research, this is gonna be very critical, and I have a hard time. In the past, I would tell you, like 25 years ago, I was doing testing in the structures lab, and we were trying to get to exactly 4,000 psi concrete, and that was big deal, and it was very expensive because I didn't want 5,000. Every time they give me, like, they say, well, why don't you come to the patch and just pick the cylinders you want and do your testing? So I went there, even for the 2,500 psi, I buy it as 2,500 psi and give me like 4,200 psi. So I said, okay, what can I do? I'm just gonna order 2,500 and hope it's gonna be about 4,000 when we come to testing. So it is not that easy to get to the concrete strength you want. You just gonna be stronger, but not lower, most likely. Another thing also for the stuff that, you look at this. It's gonna be the rebars itself. When you have the rebars, you need also to check the mill certificate order. I don't know if you guys heard about this before or not. In the mill certificate order, as you see here, you need to review the rebars, you need to review the chemical composition, you need to review the mechanical properties, which is gonna be very critical to you, right? Like what would be the test values? For example, this is grade 60, right? Look at this, it says here, grade 60, the old standard, and this is the test values, right? This is the mill test certificate. This is exactly what I'd like to look at as submitted. And if you look here, it says tensile strength is how much? This is gonna be F ultimate, and look at the yield strength. It should be 60 only. Now it becomes 66,000 psi. So this is a test value. This is what you buy. It is true that in your analysis you say it's gonna be 60, but most likely it's gonna be higher. Now the steel strength is gonna be very critical because you know that I'm working here with 615 is gonna be for gravity. But if you like to work for seismic members, reinforcing bar for seismic member, it has to be the A706. In the A706, it is controlled. You cannot just go to any value. So in the 615, your minimum is gonna be 60,000. Your ultimate, there is no limit, but yours is gonna be above 90. In the 706, you have limits. You cannot go above 68. So for example, this rebar is not working here for seismic. I cannot use this for seismic. And then the F ultimate is gonna be 1/4 times this value, times the 16. So for the seismic members, you need to work with concrete properties for the reinforcing bars, not for the concrete. Concrete is open, you can use any concrete. There is no minimum for the strength. But for the rebars, it's gonna be kind of tricky here. And of course, they give me here all rebar size, and they said, well, the weight, and they give you the tensile strength. This one is not good. You cannot use this in seismic at all. This is gonna be terrible. The yield strength is okay. I hope this helps, that you understand what information I'm gonna be looking for, and that also we need to back check all the mixtures that we add to concrete.
Yes,
Now, no problem. Now, you guys, you understand that you're going to be putting the concrete, and according to what we discussed last time, we said that you have this check on the stresses at the time of initial pre-stress, and then check at the stresses at the, I'm going to say here, the service loading case. So we're going to have here two checks. We said that we're going to have here P sub I, which means initial pre-stress, and then P sub E, effective pre-stress. You guys remember this discussion or not yet? Are we okay with this discussion or no? Not hearing anyone.
Yes.
Okay, thank you. So I'm gonna put it right here. The previous slide said, we said that we have here two conditions. If you guys remember, we have one check at the initial condition, pre-stressing. Sometimes you call it instantaneous. Pre-stressing force is gonna be P sub I, and then at the end is gonna be the effective. We said that the strength that we used here was 270 KSI. At the time of pre-stressing, we're going to be pre-stressing it to nearly 190 KSI. Later on, some losses is going to happen, it's going to be taking place, it's going to drop down to 150 PSI as the effective pre-stress. And then we said that we have limits when it comes to concrete. If you remember in the problem here, in the example, it says, here are the limits for the concrete strength. The maximum compressive stress that you can have in the concrete at service life is going to be 0.45 of V prime C. And then we say at the initial time of pre-stress is going to be equal to 0.6 F prime sub CI. And then we say CI sub CI here, or F prime CI, is going to be the concrete strength at the time of the initial pre-stress. Let's say initial pre-stress is going to happen in a week after you cast the concrete. It means that you need to figure out how much was the concrete strength after 7 days of casting the concrete. So I'm going to say, well, in our example here, if you remember, it says F prime CI was 4,800 PSI. But after 28 days, it is equal to 6,000 PSI, meaning I'm working here with 6,000 PSI concrete, but after 1 week, the strength is going to be 4,800 PSI. It's going to be lower. I said, okay. It means that every day of the concrete age, the concrete strength is going to be growing up, it's going to be increasing. And I said, yes, absolutely. So I have two issues here. If my F prime C is going to be equal to 6,000, how did you come up with this F prime CI? Is there a mathematical way of doing it, like by analysis, or is it just about testing? Does it mean that every time I have to test the concrete and figure out this before I start my design? Or how did I come up with 4,800 if I know that the strength is going to be 6,000, the final strength of the concrete? I said, well, it seemed that the F prime CI is going to be critical. This is why we have an equation for it here. It's going to be equal to fraction, and of course, this fraction, it has to be less than 1. So let me confirm this, because sometimes you can run this, and then you're getting a number more than 1. So this one is going to be equal or less than 1.0. Otherwise, you cannot really use this equation, right? So F prime CI is going to be equal to F prime C. So in our case here, it's going to be 4,800 is going to be equal to something multiplied by 6,000. This is the reason I said this has going to be equal less than 1. T is going to be the age. The same T also is going to be the age. Alpha and beta is going to be factors that depends on, I'm going to come to it. Here's alpha and beta values, factors according to this table here. It depends on the cement type. You have cement type like cement type 1, and then you have cement type 3. 1 and 2 is going to fall within the same category. This is like conventional cement, the regular cement. But if you like to work with high strength cement, something that like rapid strength cement, you're going to be going with cement type 3. And this one here has high hydration rate, meaning that this one here is going to be shrinking more than cement type 1. So I'm going to say, if I'm able here to use cement type 1 or 2, I'm going to stay with it. Also depends on the way that you cure the concrete member after you cast it. If it's going to be moist cured means after you cast the concrete, you're going to be covering it with this cure compound, or you're going to be adding water to it to keep it moist or to keep it wet. In this case here, here's the value for alpha and beta. So compare now cement type 1 to cement type 3. When you have here low factors, it means that this denominator is going to be much less. So in a case like this, once you start to use here cement type 3, it means it's going to be gaining higher strength faster than concrete with cement type 1. Look at the factors. This alpha is going to be 4 plus 0.85 times T. This is going to be 2.3. So I'm expecting this cement here to gain higher strength. And look at the steam cured. When you do steam cured, you're going to be taking the concrete member, you're going to put it in a kind of an oven, and you're going to see here hot steam that you expose the structural member to is going to be maybe for 8 hours or 6 hours or whatever, right? They have their own technology. And look at the factors that happen to them. It's going to be much less. So what does it mean? It means with a steam cured system, you're going to be gaining higher strength faster. So your F prime CI is going to be higher much faster. It means that you can do the pre-stressing faster. You don't really need to wait for the concrete strength. So when you're talking here about our previous example of 6,000 and 4,800, you would say, I need to wait, let's say a week or so to be able to start the pre-stressing or to cut the strands or to apply the pre-stressing. But you know what? You don't really need to if you're going to be having a unit to do steam curing for you. If you have this box or this oven here that you put the member through, it means that you're going to be doing faster pre-stressing. So it's going to be more efficient, because what's going to happen that you need the floor. The production floor here, you need to be ready for the next pour. So if you keep the concrete for a week, you're going to be in trouble. This is not going to be cost effective. So what happens is most likely you need either to steam cured or to change the cement type. Certainly you're going to be figuring out the cost for the steam curing and the cost for the cement type 3 to use, and then you do your math, and then you'll decide, do you really need to apply or to purchase this unit with the steam curing system, or to change to cement type 3, or just to stay with cement type 2 or 1 and just do moist cure. I mean, it's going to be up to you. Of course, if you have big open yard, you're going to say, let me just eliminate this. Let me just put them in the yard and put the cure compound and just throw water every day on it and call it a day. So it's going to be up to you. So let's look here at the age of concrete in days, the x-axis, versus the concrete strength on the y-axis. And this concrete strength is going to be in KSI. So when it says here 10, this is going to be 10 KSI. This is going to be 11 KSI, 12. So we're working here with really high strength concrete. It says here high strength concrete. Look after 7 days and after 28 days. You say 28 days, which concrete is this that you're working with? Say I'm working here with 19,000 PSI concrete. You see this concrete, this is what we call here 19,000 PSI concrete. How do I know that? I'm gonna say because the age or the strength at 28 days, right, is gonna be the strength that I name the concrete with. We call this 19,000 PSI concrete. Look at how much strength would you have after 7 days. Not bad. This can be very fast, right? So the question is, if you like to do this mix, if you like to use a 19,000, and you have the amount of pre-stressing, and you have your analytical tool, the spreadsheet or the software, and then you say, in this case, I don't really need to have a steam cure. I don't need to have cement type 3. Would my system work? If the system doesn't work, which means the structure member design is not good because you check the stresses at the instantaneous at the time of initial pre-stress and at the service, and then you don't like the numbers, then you start to change your mind. You start to specify maybe cement type 3 and then look at the test values for it. So if you like to use moist cured concrete members and you're planning to use here type 1 cement concrete, usually after 10 days, you're going to be at roughly 80% of F prime C. So this is what you usually do. So we're going to say, what does it mean by 80% of the 6,000? Can someone help me here? %80 of 6,000?
It's the strength at 7 days.
No. What I'm saying is, what is 80% of 6,000?
4,800.
Thank you. So it's going to be the 4,800 PSI. So what does it mean for me? If I really like to go into the depth of this issue, it means this concrete properties that was given to me, it assumes that it's going to be moist cured system. It is not going to be steam cured, and it's going to be type 1 or type 2 cement. And in that case, in instantaneous pre-stressing is going to happen in 10 days, which we'd like to start with because it's going to be cost effective. So you're going to be taking here F prime CI at 10 days to be 80% of F prime C. And you're going to say, we can do this in 10 days. And then you start your design. If everything tends to be okay with you in terms of stresses and flexure capacity and the whole thing, and also you think about the stages or the phases of carrying the structure members from point A to point B to the trucks to the site, and everything is good, then you're good. This is going to be a good number. You don't have any problem with. If it didn't work, you know that you need to change something. You cannot really stay with this 80% at the time of pre-stressing, and you may need to change to steam cured or maybe change to cement type 3 or maybe both of them. It's going to be up to you. So I want to keep this in mind. Usually we take F prime CI to be 80% of F prime C, and this means that you need to wait 10 days once you cast the concrete to do your pre-stressing. This is going to be the message. All right, so this is when you do the pre-stressing. But there is two things here that we need to discuss because there are going to be a big reason when it comes to pre-stressing losses. There is two things, two properties, two phenomena. One of them is called the creep, the other one is going to be the shrinkage of the concrete. You're going to say, what is the creep? If you remember the meaning of creep, for example, if you bring a beam, structured beam, any structured beam, and then you put it on two supports. You put here a point load. Once you put the point load, you can measure the deflection, the amount of sagging that happened in there. Then you say, okay, this is how much the sagging is going to happen. Deflection in instantaneous deflection, which means elastic deflection. We call this elastic deflection. You measure it, let's say half an inch. You say, good, all right, half an inch, no problem. I'm going to be taking the load out. Remove the loads. What's going to happen? Would the beam goes back straight? You say, yeah, it is elastic, right? So if you do here, elastic displacement versus load. Once you take the load out, you're going to be gaining back the same beam. I mean, it's going to be straight again. So you can recover all the displacement or deflection of the beam. But if you leave this point load, let's say for a year, This phenomenon, which is called creep, is going to happen. You're going to see here more deflection because the molecules and the particles within the concrete itself is going to start to move, and more deflection is going to happen. So we're going to call this long-term effect, and this is what you call here the creep. So the creep is going to be this inelastic displacement that happened in the beam. So for example, once you put the point load, you have a half-inch deflection. You keep it there for a year, and then you have 1.5 inch total deflection. It means the elastic deflection was equal to 0.5 inch, and the inelastic or the creep deflection is going to be equal to 1 inch. So both of them is going to be equal to 1.5 inch. Are you guys following me? Yes? No?
Yes.
Okay, good. All right, so let's say after 1.5 years, I have taken the load out. I removed the load. Would I have any deflection left? You say yes, because you have the elastic deflection was equal to 0.5 inch. Once you take the load out, it's going to come back. You can recover it. But the inelastic displacement is going to be locked in, which means that you're going to have permanent deflection of 1 inch. You cannot get this back. It's going to stay there in the concrete. And this is what you call here the creep. Let's look here at this curve, try to understand what is that. This can be the time of loading. Time after you put the loads in days. And this can be the amount of strain. We call this the creep strain. Like in our example here, I just related to deflection. And of course, if you have deflection, you can figure out the strain in the concrete. You can do your math. Once you apply the load, what's going to happen? Look what happened. It went up. What does it mean? This can be the elastic strain. It happens right away. And this elastic strain, let's say about 220 microstrain. All right. With time, you see what happened? The strain is just grown. This is the time, and here's the amount of strain, long-term strain. We call this going to be the creep strain, which means the value of the strain from here to there. And here's the performance curve. It's going to come to a point. You go here to the next page. So at the beginning, I have this elastic strain. Elastic strain is going to be roughly from here to there. It's going to be this amount from the bottom to here. Once you start the load, it's going to happen all the way to here. It's going to be more detailed. And then you leave it loaded. You leave the beam or the structural member loaded. What's going to happen? You're going to have here increase in time, and then you're going to have here lots of inelastic strains. Now at this point, you're going to be doing unloading, which means that you take the load out, remove the load. It's going to be only one load value. Let's say that you put 10 kips, you just remove the 10 kips. What's going to happen? You have this instantaneous recovery, and this amount is going to be equal to the elastic strain. You see this value here from here to there, this amount from here to here. You're going to be recovering this. How much is this? If I take this number here, look, this number is almost like in here. Meaning, when I said at the beginning, when I gave the example, let's say that I have a beam, I'm going to be loading it with, let's say, 10 kips as a point load in the middle. I just assume that the total 0.5 inch is going to be elastic deflection. But you know what? Not the whole 0.5 inch elastic deflection. Because it depends on the strain level I'm going to be approaching or reaching to. You know that at the beginning, at the early stage of loading, you're going to be in the elastic range of the concrete. But let's say that I put a point load which is close, let's say, to the capacity of the beam. So I know that I'm going to have some inelastic strain that's going to happen instantaneously without even waiting. Meaning, you see here, if you look carefully at this line, if you look at this one, all the way to here, this gives me the amount of strain or deflection that you consider to be elastic. And all the way to here, look at this, it says instantaneous strain. The difference in strain between this sloping line and between this vertical line, the datum here or the axis, this amount of strain here, this is not because of the time elapsed. This is going to be because of you're taking here the structure beam or the structure member to the inelastic strain range. If you remember here, the concrete stress, if I may go back here, stress strain relationship for concrete, it looks like this. So if you apply a point load, it's going to be taking the strain only to this range. It's going to be all elastic. Look at this, it's going to come back. But the problem, if you put here, some load is going to be taking the concrete strain all the way to here. Now the concrete has deformed already, and it's going to keep this deformation in there. So maybe the first amount of strain that you called here elastic, you can recover it back. But the rest of the strain, which means from here to there, you cannot really recover it back. And it's going to happen instantaneously. You don't really need to wait. This is regardless of the creep phenomena at all. So as it shows here, that once you start the unloading process, now you take the load out, you're going to have all of this recovery. Some recovery is going to happen right away, which is almost all the way to here. And then some other recovery, because same thing, very similar to what happened at the beginning. You forced the concrete under this load to start to deform due to the creep, due to this long-term effect. Now, once you take it out, it's going to take some time before it gives you back some of the strains. And then at the end, after a certain amount of time, you're going to have this strain, which is going to be locked in within the concrete member itself. We call this the permanent strain. Does it make sense? Hello?
And that's like after 28 days or well in the future?
No, this isn't going to be in the future. Let's say that you kept it here, you kept the loading for 3 months. And then you need maybe another month before you have this permanent strain value to be in there.
Hmm.
So we're talking here about long-term thing. It's not going to be like just 28 days.
Got it.
Yeah. And this can be for years. You can keep this for years. It's going to be grown up, right? And then at the end, you're going to be leave it or undo the unloading, take out the stresses, right? And then it's going to be coming down like this. If this is just a straight line, right? It become, let's say, this way. And then this curve is going to be repeated. So the curve is going to be doing this. If this makes sense to you.
So if you never unload it, the strain will stay high.
If you
But
never
if-
unload it, or if you never unload it, it's going to do this. It's going to just continue to a certain point. So
And then
this
if you
is-
unload it and reload it, will it be any difference? Will it not get to that original?
Yeah, absolutely. Let's say that it's going to be going like this, okay? It's going to be going till it hits this line. All right. But let's say that you load it, unload it, you load it, unload it. It's going to be doing this. Then you load it again. It's going to be doing the same thing. It's going to be repeating the same curve.
Oh, okay.
So you see this curve again, it's going to happen here. But this is going to be the starting point. This is going to be actually a very good point that you're raising here. What happened if you load it and unload it, right? All what you need to do, just take a copy of this curve and put it to start from this point. Again.
That's where fatigue comes in and it could
Yes,
ultimately
exactly.
fail.
Yes, exactly. But this is going to be called low cycle fatigue and it's going to be slow fatigue. Because this is not dynamic stresses, right? This is unlike seismic. And seismic is going to be completely different. It's going to be something that we call hysteretic performance of concrete. So all of that is going to be low cycle fatigue, and it's going to be, we call this quasi-static, as if you are applying just a static load. It looks like a static load, right? The load stayed there. It's not dynamic load by any means. This loading and unloading thing. Because you keep it, let's say, for 2-3 days. You cannot call this dynamic. Dynamic force, you're going to be having change here in the force direction and magnitude, maybe in a fraction of a second, like in earthquakes.
And with
different performance. Yes.
With seismic, is there more of an emphasis placed on the performance at the joints instead of the entire member?
Yeah, because the joints is going to have the higher stress.
Yeah.
let's say in a beam, right? Where is the maximum moment if you have fixed ends?
The reaction.
It's gonna be at the end. So this why the connection is gonna be very critical, right? You're absolutely correct. Any other questions? You're good? All right. So now we have an idea about the concrete performance when it comes to sustained loads. We call this sustained loads, which means permanent loads. Loads can be staying there for a long time. All right, now let's talk about shrinkage. This is very complex here. I mean, complex phenomena if you like to discuss it. And how would you figure it out? We call this drying shrinkage. Because what happened when any cement is going to start to dry, which means a hydration process is going to happen, you're going to see some shrinkage. All cement is going to be doing this. But you know what? The concrete member itself is not composed of cement only. So you don't have cement only. You have cement, you have aggregate, you have admixtures, you have reinforcing. You can say, well, we are talking here about the concrete. Why do you bring the reinforcing into the picture now? Yes, say shrinkage is going to happen to the entire structure. And when you have reinforcing you keep the structure size. So the reinforcing will start to stop, or will try to stop the concrete from being shrink. So this concrete here, it wants to shrink for the cement as a material. But having the reinforcing cage inside the concrete is going to resist the shrinkage process. So say here's the amount of strain, and here's the time. We understand it's going to be growing fast at the beginning, and then it's going to slow down with time. So, okay, good. So what is this based on? I'm going to say number one is going to be based on, number one is going to be the cement type. The rapid strength cement, the rapid strength cement will have higher shrinkage properties. Okay, so it's gonna be number one, which means for each cement, I'm gonna have different like set of curves like this. Number two, the aggregate. When you have lots of aggregate, what do you expect? Would you have more shrinkage or less shrinkage? Don't forget, I'm talking here about cement and aggregate. You put them in a mix, you put concrete. The cement is a shrink material, a material that wants to shrink. And the aggregate is resisting it, resisting this shrinkage. So when you put more aggregate, like by volume or by weight, it means you're gonna have this shrinkage. And this is gonna be number one. Look at this. On the x-axis is gonna be water cement ratio. On the y-axis is gonna be the amount of shrinkage as a strain. Look at this curve here. Let's say I'm gonna be at 0.45 cement ratio. What happened here when I have 80% of the volume to be in aggregate? When I have 80% versus 70% versus 60%, look at the amount of strain. You add more aggregate, shrinkage would get less. So we can say this is gonna be very important, right? Your concrete makes design for pre-stress. So yeah, now it's gonna be critical. I need to pick the appropriate mix design for my work. I'd like to add more aggregate as much as I can. At the same time, I'm looking also for higher trends. Meaning I need to look at the mix design and pick the one that has high aggregate portion or percentage. At the same time, I'm looking for certain strength. This is gonna be tricky here. I need to balance my choice. Other thing here is gonna be also the aggregate type. The rock itself, it is gonna be different when you take it from a spot to another spot. It depends on the supplier. Because we said that the aggregate itself, it's true, it is resistant to the shrinkage process or the phenomena, but you need to understand also that some aggregate is gonna be also shrinking. So generally speaking, you'd like to go with less shrinkage properties when it comes to the aggregate. And we do this. In the concrete mix design, they give you the properties of all the aggregate, and then they give you the shrinkage properties. And I showed this to you. So the shrinkage characteristics or properties of the aggregate is gonna be very important. So the aggregate type and the amount of aggregate These two items gonna be very critical. What's the other item that we need here to look at? Is gonna be the amount of water that you add to it. When you add lots of water, and you're talking here about drying process, it means this property or this percentage of the concrete volume is going to start to reduce. Why? Because you're going to be losing the water. Once you lose the water, it means what? Shrinkage is going to happen. When you have lots of water and you lose it, it means that you're going to have more shrinkage because the volume is going to be shrinking more. This is the reason that once you start here to add more water to cement ratio, when the amount of water itself is high, what happens to the shrinkage is going to be higher. You try to reduce the amount of water as much as you can. And definitely you can do this by adding some admixtures, something to increase the workability of the concrete. Because now you are taking here a big element. You're going to be reducing the amount of water. So how would you mix it? How the water is going to be flowing and getting inside the formwork and vibrated. It's going to be very tough when you have low water cement ratio. Just so you know, if you go here with water cement ratio of roughly 0.5, for you, if you look at the concrete, you feel it's very solid. And you would say, I cannot really use it. You'd say to yourself, if you look at concrete with water cement ratio 0.5. So 0.45 is going to be very low. And you cannot really work with the concrete unless you put good additives. It's going to be either air entrained or something for the workability, like the WRDA. Also, the concrete member size is going to be affecting the amount of shrinkage. Let's say that you have very thin slab and look at the amount of shrinkage. And also the rate of shrinkage is going to be completely different. Also the ambient conditions like the temperature and the humidity. Would you compare here a pre-stressed beam and let's say with Arizona? I'm not talking here about the aggregate because of course the aggregate is going to be completely different. Concrete mix design here is going to be different than there. But I'm just saying here, if you have the exact same beam and you put it to dry here in California and you put it to dry in Arizona, which conditions do you think that you're going to have more shrinkage? Is it here in Arizona? I say, well, Arizona is going to be very dry. Drying process is going to be faster. And generally speaking, when it's going to be very dry, it means that you're going to be losing lots of the moisture inside the concrete very fast. So I would say, of course, Arizona, you're going to have more shrinkage, meaning more losses. This is going to be a problem here for you. When you design a structure, you need to understand where would you put your design at. The structure, location is going to be very important. So you can figure out the concrete mix design, you're going to figure out the shrinkage, the creep, and the whole thing. You need to figure this out. The reinforcement. Here's the third item in this slide. You put more reinforcing, what do you expect? Less shrinkage or more shrinkage? I understand that reinforcing itself, once you put the cage inside, is going to be resisting the shrinkage process. So you're going to say, well, I put more reinforcing, it's going to be less shrinkage. Some people would do pre-stressed members and they put more reinforcement at home. Like in some precasters, they don't put any reinforcement. So what do you expect? Yeah, it's true, it's going to be cheaper because you don't put this non-pre-stressed rebar, the conventional rebars, but it means that you're going to have more shrinkage. Once you have more shrinkage, it means more losses when it comes to the pre-stressing. So there's the balance. You need to figure it out. Should we add a little bit of reinforcing? Or we should not add any reinforcing and just leave it like only pre-stressed? This is going to be their call. Admixtures. Like, you know, the calcium chloride. It accelerates the drying process. It makes it faster concrete. So therefore, the shrinkage rate also is going to be higher. The rapid trench concrete, the type of cement. Once you use this cement type 3, what's going to happen? You're going to have higher trends very fast. Nothing for free. You need to pay for it. Not just the cost, but also when it comes to properties. So you gain higher trends, it means that you're going to have here high shrinkage. So you need also to work on the amount of pre-stressing losses if you want to. Also the carbonation, which is this chemical reaction between the carbon dioxide and the cement itself. Well, anyways, the total strain, epsilon sub t, which means the total. I'm gonna go back here a few slides. This one here that we use for the creep, right? So we have the creep strain, which means inelastic deformation, inelastic strain, and the elastic strain. So at the beginning, once you apply the load, you're gonna have this elastic strain. Number two, you're gonna have the creep strain. In the same time, you're gonna have also the shrinkage, because shrinkage strain is gonna happen also over time. So let's say after time t, which is estimated here to be, let's say, a year, after 1 year, what's gonna happen? Now you need to figure out or calculate or come up with the value of the total shrinkage. You're gonna say, well, total strain is gonna happen in the member. It's gonna be equal to the following. Elastic strain, yeah, once you apply the load, and the load in this case is gonna be the pre-stressing force. So once you apply it, you're gonna have this elastic strain. Over time, the concrete member also is gonna start to shrink more. It's gonna get shorter. Why? Because the creep. So this is gonna be long-term deformation under sustained load. On the top of that, you're gonna have also some shrinkage because the member is gonna start to shrink. So all of that is gonna be additive because all of this is reducing the member size under the pre-stressing force. So here's one example for a structure member exposed to compression force or stress of 900 psi due to pre-stressing. Look at the immediate elastic strain. It's gonna be the elastic strain was gonna happen right on. It's gonna be, let's say, 250 units. Of course, it's 250 microstrain. Plus, the shrinkage is gonna be about 500, which means shrinkage is gonna be double the amount of strain is gonna happen due to elastic loads. So the elastic strain is gonna be 1/2 of the shrinkage. And look at the creep. The creep is gonna be 1.5 times the shrinkage. So I'm gonna say which one here is the most critical one. I'm gonna say the creep. How would you control it? I'm gonna say the aggregate and the amount of reinforcement that you put in there. This is gonna be general terms, right? How about the shrinkage? Yeah, shrinkage is gonna be very important. Look at the value, two values. 1250 for both of them versus the immediate elastic strain. So the immediate elastic strain is really low, but it contributes, right? It is 250 out of 1500. So now you have the feeling by just looking at these numbers, which one is gonna be the most critical strain. It's gonna be dangerous to you when it comes to losses. Yes, it's gonna be number one is gonna be creep, number two is gonna be shrinkage, and then number three is gonna be the instantaneous or immediate shrinkage. Any questions? Hello? You guys here?
No question.
No questions.
Okay. Let's take a small break and we'll come back. We stopped at the concrete strain and how this is going to affect the losses. And we said that we have the total strain is going to be composed of 3 components here. You have the elastic strain, which is going to happen right once you apply the pre-stressing to the concrete. And then you're going to have the creep strain, which is going to be due to the fact that this pre-stressing force is going to stay there for a long time. So we call it, in this case, sustained loading on the structural member. And then plus the shrinkage, which is a nominal phenomenon that happened to all concrete structures. And certainly adding reinforcing, non-pre-stress reinforcing is going to be reducing the amount of shrinkage and creep and elastic strain that may happen. And of course, it's going to be reducing the losses. Now, when we're talking here about the time of pre-stressing reinforcement, we have wires, and then we have strands, and we have also bars. So we have all types. The one that we'd like to work with is going to be the one with 270 psi. This is going to be kind of very common. This is what you see in the market. This is the one that's going to get you a good design, like an optimum design. So we'd like to use it. So the 3 types, you have wires, you have strands, and then you have bars. I'm looking here, it says uncoated stress relieved or low relaxation. So it's going to be uncoated. There is no coating to it, right? Uncoated, uncoated. High strength steel rebars. So it's going to be like regular rebars, but it's going to be usually large in size, And it's going to be higher trends. It really goes to higher trends. We're going to look now at the values. Now we have wires and strains. Now I'm trying to understand the difference between a wire and strain. A wire, you take few wires, you twist them together, they become a strain. So the strand is few wires twisted together. Now stress relief and low relaxation. We'll learn very soon that low relaxation is going to be like low, is going to show you here less relaxation. And in a case like this, of course, then the stress relief. And in a case like this, it's going to give you here less losses, if you like. So the three types, according to the code here, the pre-stresses, strains, wires, and bars, according to the ACI code, you have the strain is going to be conforming with the ASTM A416. So as you know, this is going to be the specifications. And earlier, I have discussed the difference between the code and between the specification. When it comes to specification, the A416 is going to be this document, is going to include all properties of the strains that you may code here 416. Properties means chemical properties, mechanical properties, shape and size, and color and the whole thing. In description for it, so that once you have here a piece of the strand, you can go back to the specification, do the testing and everything on it, chemical and mechanical. And once you satisfy it, it means that this piece of strands conforms with the 416. For the wires, it's going to be conforming with the 421. I'm going to jump here to the A722, which is a higher trends report. So this is going to be the three common, I'm going to say here, cables or strands or system, reinforcing system that you can use here for pre-stressing. The very common one that we'd like to use, and we're going to keep on using in this course, is going to be this one, the strands. This is what people use in construction industry. The high trends bars, they're used. And you're going to see them, let's say, in the structures lab. You're going to see in certain applications. You're going to see it in like railroad construction. If it comes to pre-stress, you're going to see it in metro projects. You're going to see this high trends rebar, and yours is going to be a big in size. So we're talking here about more than an inch. So the standard that you're going to see there may be an inch, inch and quarter, inch and 3/8. So this is going to be real big rebars with high strength. This one you really need big force. The strand here, the very common size, going to be like an 1/2 inch. So you cannot really compare this to this. It depends on the amount of pre-stressing that you want to apply. So in infrastructure, generally speaking, we can use this. What's the process? How do we do it? We bring here the base material, which is going to be this round bar. They're going to be patting it, which means they're going to be heating it to 1470, and then they cool it slowly to make it homogeneous. So it's going to be heat treatment, as you see here. They heat it, and then they let go. And then after that, they draw it through this die. What's going to happen? You put lots of pressure on it, and the strength of it is going to get increased by pushing it through a die. They pull it, actually. And once they do this, now they have wires. And once they have wire with this process, we're going to call it the 421. So up to this point, you're going to have the strands, which means the 421, the wires. You don't have a strand yet. So what do you do after this? You bring the wires all together. You're going to be twisting them, put them all together. And this is the process here is called the stranding. So how does it work? You put one in the middle, which is the cord one, and then you put 6 around it, and then you start to twist them. And with that, you're going to have something like this. If I may zoom in, just to show the picture. You're going to have 6 and 1 in the middle. I said, okay, now I call the strand. So what is a strand? It's a bunch of wires, all twisted together. So all right, it's just a strand. Now it is not 416 yet. To make it at 416, I have 2 phases. Or if you like, I have 2 options. You do one of them. The first one is going to be the stress relieve the strain. How do you do it? You heat it to about 660 and then you let go. You let it cool slowly. And you say, okay, good. Now I'm relaxing it, right? You're doing the stress relief here. This is good. Now it is 416, you can use it as is. Some people would do it differently. The other option, you heat it, but first you apply tension to it. So you put it in tension, you apply the heat, and you let it cool down. So which one do you think is going to have higher properties? Is going to be the stress relief or the low relaxation? Without even understanding the reason. I'm just telling you here that we have two options or two different processes. Which one do you think is going to give you here less relaxation, which means less losses? Guys, are you awake?
I think the stress relief strand, we're gonna have higher, not that much of relaxation.
So which one is better if you have the chance, the choice?
So I think the low relaxation strand, because less loss probably.
Yeah, why do you think it's going to be less loss? You're absolutely correct, but I mean, I'm trying to see how do you feel about it. You don't need to give me a physical reason, but just the feeling,
Is it maybe the strand is already under tension?
Yeah, I mean, why would they put tension? Someone's gonna say, why would you put tension? Just do it this way, right? There should be a value by doing this. When you do more work on the same material, it means that you're gonna be gaining better properties. And this is exactly what happened. Because I can simply say, why the bother? I mean, why would you just put it under tension? Just heat it up and let go. Because to put it under tension, you need equipment, it's gonna cost you. So there should be a good outcome out of this process. And this is absolutely correct. Low relaxation strains is going to give you here less losses when it comes to pre-stressing losses. Good. So here's what's going to happen. The 421 is going to be stress relief. Why stress relief? Because look what happened. We're going to be heating it and let go, right? It's going to cool slowly. So here we're reducing the stresses, right? And once you put them all together, it's going to be the 416. So okay, this is very good. Here's the 421 properties, and here is the 416 properties. I have here table of properties. Look at the 416. Look at the 421 first. It's gonna be all wires, right? This is gonna be all wires. Look at the wire diameter, like 1/4 of an inch. It's not gonna be really that big. Look at the tensile strength. I can see this. Look at 1% elongation, right, or extension. Look at the amount of stresses. You extend it 1%. Don't forget, when you apply the pre-stressing, you don't really apply a force. You pull the cable and then you put the anchor. So pulling the cable means that you put a force to the cable. So you apply an extension, and therefore it's going to be converted into compression force on the structural member, on the concrete member. So here's the 421. Then you say, where do you think I'm going to apply this? What structural members? You say maybe in blanks. The hollow block. If you remember the hollow block, the one that has circles, like the concrete slab. The short span, maybe I can do wires in there. I'm not going to do strains. Then this is going to be very good for that application. Only for small spans and small work. In pre-tension, not in post-tension. So this, generally speaking, is used for pre-tension. It's going to be for small construction and small spans. Now let's look here at the 416. I have two grades, 250 and grade 270. Of course, I'm going to be working with 270. We mentioned this before. This is going to be our choice. It's going to be 270. And what bar size, generally speaking, I'd like to use, you say either 0.5 or 0.6. Which one is more available in the market? Which one that you're going to see it and you can specify it safely? You say is going to be this size here. Look at the cross-sectional area of it, 0.153. But it's going to be 1/2 inch. When you look at 1/2 inch rebar, if the rebar, conventional rebar, when you look 1/2 inch, you guys remember the square footage? Let's see, square inch is the cross-section area for number 4, like 1/2 inch. Number 4, how much is AB? Anyone remembers? AB for number 4?
0.2.
0.2 square inches. Look here, 1/2 inch. which is the same as number 4, but it's gonna be 0.153. What is the reason of this? Because this is composed of all solid material for the rebars, right? But this one is not. Look at the way it looks. It looks like this. You have 6 wires around 1 in the middle. So you have some voids in the middle here, right? So this is why the net cross-sectional area of the strand is going to be equal to 0.153. This 0.153 is going to be for all of them, for the 7 strands, so 7 wires. So you have the 7 wires, they compose 1 strand, and they have total cross-sectional area of 0.153. Said, okay, good. All right. So what happened? We have also another 779. What is this 779? You take the strand, like one of the strand, and then you start to draw it, right? You start to draw it, which means that you're going to put pressure on the outside of it to make it more condensed. And look at this. At the end, when you have half an inch, look at the cross-sectional area, it's going to be 0.174. How does this happen? I mean, this half an inch is completely different from this half an inch. If you take this like 0.6 of an inch, which means 0.27, or some different values, you're going to be taking here different wires, put them together, put them through, draw it, it's going to give you this cross-sectional area of half an inch. It's going to be, let's say, 0.174, or quarter. If you're going to go here is 0.6. So don't think that they're going to be taking the 7-wire strand of the 416, half an inch, and convert it into the half-inch A779. It's not going to work this way, right? Because the diameter itself is going to get reduced. But if you like to go with the 7-wire strand, the 779, half an inch, you're going to have bigger cross-sectional area. And the difference in cross-sectional area is kind of significant, because when you compare 0.174 to 0.153, there's some difference. So it is nothing that you can just ignore. You have here increase. But this is not very common. So in my course here, I will avoid the use of it. And most likely I'm going to stay here with a half an inch, the 416. This is what we'd like to use. Also in the 722, you have this Dewey-Dag bars, the big deformed bars. And look at the size, can go all the way to 1 1/4. So you have 1 1/4 of an inch solid rebar. Look at the cross-sectional area. This is a lot, 1.3 square inches, roughly 1.3. Compared to your half an inch of the strands, 0.153. How many strands are we talking about? Maybe 9 strands? This is going to be equivalent to 9 strands in 1 bar. Just this is, I mean, this is very strong. So you're not going to use it in concrete slab, right? You're not going to be using it in concrete beam in a parking structure. Maybe using a big bridge. Yeah, you'd say yes. Or maybe a bigger structure. Let's say that you have big pipeline and you need to have big supports and you need to do some pre-stressing. Then in this case, you'd use this, because the use of this is going to be nonsense. The use of the regular strand, the 7-wire strands, the 416, it's not going to be good. So in this case, you stay here with 722. This is different alloy. As you see here, the grade is going to be like 150 or 160. We call this Dewey-Dag bars. This table here does not include the 1 3/8 of an inch, but I personally have used the 1 3/8 of an inch. This is there. Manufacturer would carry the 1 3/8 of an inch and 1 1/4. It depends on the manufacturer. I have seen a lot of 1 1/4 of an inch available, so this is easy to find. 1 3/8 of an inch does exist, but it's not easy to find. Any questions? We're good. Move forward. Okay. Here at the table give you the tensile strength. So all of this is going to be just based on the available, I'm going to say, information and data, right? Different tables and stuff like this. But here what the code says. The code says this is going to be the available options if you like to go with this design. You can go with the strength, the stress relief, and low relaxation. Of course, low relaxation is going to be less impacted and less effect on the losses, and it's going to be 416, it's going to be 270 KSI. You can use the 421, it's going to be 250. You can use the A722, it's going to be 150 KSI. So even when I see this, without thinking, it says here from what? From 145 to 160, but I know usually we use it as 150. We call it 150. So this is gonna be 150 KSI big rebar. And of course you can go 1/4 or 1 3/8 inch, which is very common. Okay, good. This is what the code says. And here's the code section. How about the performance? How would I look at the performance and E and all of that? And here's a comparison here between the 416 and between the grade 160 alloy bar. What's the grade 160 alloy rebar? You say is something like this. So here's a mild steel. You say mild steel, you're talking here about FY of 6 KSI. Look at this, 40 and 60. You say, yeah, they called mild steel. Look at this. Here's the performance of it. A stress-strain relationship. Look at the pre-stressing strength. It goes all the way to what? The 722. Pre-stressing steel, FPS, but we use it as 150. Okay. Now let's look at this. Here's a comparison. The 160 versus the strength that we usually like to use. Yeah, this give you the strength, this give you your 416. This is a one. 270 KSI. Look at 270 where it happens. It's gonna be the strength that we use. Do we really stress it to that number, to 270? I'm gonna say no, we stress it only to 189. Effectively to 150 KSI. All right. How do you relate the yield strength to the ultimate strength? Where's the yield strength? I'm gonna say here's the yield strength. We consider this to be the yield strength. It's gonna be based on the 2%. If you remember the 2% offset, I don't know if you guys remember this, the sloping line. Because you're gonna say, how would you define here the yield strength for a rebar like this and doesn't have a plateau like this? There's a way of doing it. So the code here says the ratio of the yield strength for the pre-stressing to the ultimate strength for the 416, which I really care about, the stress relieved, which means the lower grade is gonna be 0.85 or more, which means yield strength is gonna be very close from the ultimate strength. But for the low relaxation, which is a higher grade of the 416, is gonna be 0.9, at least. You say, is this important to me? Because all what I care about for now, this is my understanding. I'm gonna have 270, 189, 150. This is the three numbers I need to memorize. As long as I'm gonna be doing here pre-stress. Three numbers again. 270, 189, 150. Some people would say 270, 190. I'm okay. I mean, 189 to 190 does make a big difference, right? But I would say 270, 189, 150. And the yield strength, 85% for the low grade of the 416 and 90% for the low relaxation, which is a higher grade A416. Okay, good. Let's keep this for now. We'll figure out the reason that we need this. The 722, I understand that this give you the bars, like the duodec bars, but we're not gonna be really using it. So I don't really care about these two numbers for now. Okay. FPU, which one is this? I guess say this one, absolutely, is gonna be the 416. ASTM A416. What? Strengths. This is what I care about. This is what I'm gonna be working with. So this table is made specifically for this. The ultimate is gonna be 270 KSI. This is gonna be the tensile strength specified. This is not the test values. This is a specified values, which means the test value is gonna be higher than this. Otherwise, you cannot really use it. This is gonna be the minimum specified. The yield strength is gonna be 229 and 500 PSI, which is 85%. If you run the numbers here, I'm gonna say, well, this is gonna be 85%. So what does it mean? I'm gonna be using this. So most likely I'm gonna be going with the lower grade of the 416. I have here two grades. I have the 416, the stress relief or low relaxation. The stress relief is gonna be cheaper. So it's gonna be less cost. It's gonna be more available. So if you plan to go here with 416, try this one first. If your design is not good and you're in trouble, you're gonna be going here to this low relaxation. But you need to understand that you may not find it in the market, or it's gonna be a little bit pricey. So I'm gonna say here, stay with this one. So I'm gonna be using here the 85%. I said, well, This is the one that I'd like to use. I said here, if I take here 270, multiply by the 200 by 0.85 according to this table here, I'm going to be getting 229 and 500 KSI. It's going to be the yield. And instantaneously, I'm going to be using 189. And how much is 189? When you compare to the yield, it's going to be 82%. So first, I'm going to be taking 85% of the ultimate. Then multiply it again by 0.82, 82%. To get what? To the instantaneous or the initial pre-stress. And then you take 70% of FPU of the 270, is going to be the 189, is going to be also FPI. And if you run the numbers, take 0.82 times 0.85 is going to be equals to 0.7. Now I understand where the 0.7 is coming from. So some people would say, take 70% of FPU because we're expecting a loss of how much? They say, where's the losses? We're not talking here yet about losses. So we're going to say, oh, we are talking here about the 150, which is the losses. How much was the losses between 150 and 189 again? I guess you guys calculated that before. How much was the estimated losses?
20%.
20%. Is this true? You can say, yeah, just try this. You can say 150 divided by 189. It's going to be 0.794, which is very close. I'm going to say maybe 20%. This is going to be the estimated value. So okay. Relaxation. How can you figure out the relaxation? What does it mean by relaxation here? You take the rebar or the strand or the wire, any one of them, you apply tension to it. I'm sure that you're going to have extension, right? Once you apply the tension force, you're going to have elongation. And then you leave it there. You leave it for a month. You leave it for a year. The amount of strains that you put in there in the rebar is going to get less and less and less. And this is also going to be part of the 20%, the losses. So all the losses here, it's not going to be only due to shrinkage, instantaneous or elastic shortening. The elastic shortening, which means the elastic strain, by the way. We call this also elastic shortening, known as AKA. So you have the elastic shortening, which means initial shortening of the concrete or strain. You have the creep, you have the shrinkage. It's going to be all about what? The concrete as a material. We have also mechanical losses. We have slippage in the anchorage at the beginning, at two ends of the concrete structure. So you are going to have a little bit of mechanical losses. We call this mechanical losses. And what else? The elongation of the rebar itself. The rebar is going to be losing the strain that you put in there. It's going to be relaxing a little bit. And there is a way to figure it out. All of this equation that you're looking at in terms of F prime Ci and for example, in terms of the concrete age, alpha and beta and all of that, this is all empirical formulas. It's going to be based on testing. They do testing and then they come up with the best curve that's going to be fit. So you do the best fit curve. I mean, there is no analysis behind this. You cannot come here and say, well, this is going to be based on analysis. I'm going to say, what analysis? This is going to be based on testing and figure out an equation to represent this type of material. So all of this, they are all empirical formulas. So for the normal relaxation, which means the regular cables or the regular strains, it says delta sub FR is going to be equal to FPI multiplied by a term here. So okay, log T, which T is going to be the time an hour divided by 10, and then FPI divided by FPY. So FPI and FPY, I guess now I understand the importance of this FPI. Because calculation of the losses is going to be based on the stress amount of the stress value that you put divided by the yield strength. Yield strength here is going to be an issue. This is why this yield strength is going to be an issue to me. This FPY divided by FPU 0.85 is going to be for the stress relief. For the low relaxation, it's going to be 0.9. Is this important here? I'm going to say, yeah, think about 0.85 minus 0.55 versus 0.9. Which one's going to be keeping the stress more? Say, well, this is going to be an issue, right? We need to be careful about this. Here's the same expression. I'm just repeating it here again. And then we're going to say here, this expression is good as long as FPI divided by FPY is going to be more than 0.55. I say, let's look at the standard, just to be careful here. What is the standard when you compare FPI divided by FPY? I'm not talking about this. This is going to be FPY divided by FPU. I'm talking about FPI divided by FPY. You can see, what ratio did we use? What's the ratio between FPI and instantaneous to the yield? You can say, I have used 82%. Good. This is going to be more than 0.55. So I'm good. I should be able to use this equation. Why 0.55? Because look at the equation. This can be empirical formula, right? This empirical formula, it says FPI divided by FPY minus 0.55. If you put FPI divided by FPY to be less than 0.55, it means that you're going to have a negative value. It doesn't make any sense. So you shouldn't be using any value of FPI divided by FPY to be less than 0.55. You need to have enough stress in the strands to start with. And it's going to be greater than 0.55 of FPY. Otherwise, don't use our equation. So someone's going to say, how about if I have a beam and the amount of pre-stressing was really low? I'm going to say, they didn't test it for this because this is all based on empirical formula. No one came up with analysis, let's say, for the stresses and came up with this equation. No, it is completely different. Now, here's what we have used. We have used FPI to be 0.82 of FPY. And this is exactly what we have used. And we said that FPI is going to be equal to 0.74% of FPU. We did all of that. I said, okay, I should be able to use this equation now. This is for, now for the low relaxation steel, I'm going to be changing my equation. So FPI divided by FPY is going to be the same, but look at this. That was log of the time T in hour divided by 10, right? The time is going to be T in hours, right? But this one is going to be log T divided by 45. You say, what does it mean for you? If I just give you here two equations, I'm going to say one of them is going to be for the stress relief, and the other one is going to be for the low relaxation. Which one is going to be performing much better for you? It's going to be this one or this one? Look at the equation here. The amount of losses that you're talking about is going to be equal to FPI. You say, okay, FPI in both cases is going to be the same, right? I'm going to have the same strengths. They're all 416, 270 KSI. One of them, it says FPI divided by FPY negative 55, and the other one is exactly the same. So there's no change here. One of them, it says log T divided by 10, the other one says log T, which is the same, divided by 45. So which one here is going to give you less relaxation or less losses? You say, of course, it's going to be this one. By how many times? You say by 4.5 times. Look at the value here, the ratio. 45 compared to 10. So I'm going to go back here, if you don't mind, to this slide. Let's say, look at this slide here. If the amount of losses that you have in this system is equal to 1, the amount of expected losses here is going to be 4.5 times. I guess this is now significant, right? How about the 20%? I'm going to say the 20% losses just calculated for this system here. So if you don't like the losses, or let's say if you move to another state, let's say that you're working in Arizona, and you have lots of shrinkage losses and creep losses in the concrete because the supplier and the concrete nature and the ambient temperature there and the condition there, then maybe it's a good idea to switch to this system here. Why? Because it's true that you have losses, higher losses due to shrinkage, but you can reduce it by using the low relaxation strength. Does this make sense or what?
Yes.
Okay, thank you, Ron. Is it okay? Do you think I'm going to be using really this when it comes to my analysis? I'm going to say no, not really. When it comes to design, you don't really do this. When it comes to actual practice, we don't touch these equations. We just say it's going to be 20% if you use this system and use this aggregate, and that's it. If you have a special case, let's say that all of a sudden you're moving here to a new area, you don't know exactly how much is the loss is going to be, or you like to figure it out, it's going to be a different story. In a case like this, you need to figure out the elastic shortening, you need to figure out the creep, shrinkage, and then you need to figure out the relaxation. And then you need to work with it. You need to figure out, does it make sense that I need maybe to change the structures that I work with? Do I need to change the materials? Do I need to change the strengths? Does it make sense? Or I should just stay with the system I'm used to? So here in California, we're using 20%. We're using here the stress relief, just to make it simple. Okay. Look at the amount of losses. So relaxation, stress relief. Let's say after 1,000 hours, what's gonna happen? You can compare here. Don't forget that this is your log scale, which means big difference, right? Look at this number here. How much is this number? Someone can help me. How much is this compared to this? So let's say if I move the line right here, I'm gonna move this line right here, since this is logarithmic scale, I'm gonna move it here. And say, let's talk about this line here. How much is that? Well, they say maybe about here's gonna be 4.5 times, but the way I see it here is gonna be 1, 2, and 3.5, right? Don't you guys agree?
Yeah.
But according to this equation, it says 4.5 times, which is okay. I mean, I'm okay with this. This is the way it is. Now we have here a big issue about the corrosion, right? And deterioration of the strengths. We need to protect them. Is there any way to protect them? And why it is important? Because what's going to happen if you have any corrosion, it means that you lose a section of the cross-sectional area of the strength. And you know the way that we figure out the amount of pre-stressing force. You have the strain. Once you have the strain, you figure out the stress, multiply the stress by the cross-sectional area of the strain. Now you have the force. Now, when you lose a section of the strain, it's getting smaller. When the wire is getting corroded, what's going to happen? You lose the pre-stressing force. So you cannot just leave it this way. You need to protect it. Now the question is, what's the protection that you can do? A big issue here when it comes to protection that you can do is going to be in your design. You can design the structure to be free of cracks. And if you do this, there's not going to be any moisture intrusion or any chemical intrusion to the rebar. We do this a lot when it comes to water structures like tanks, water tanks. You do it this way. So let's look at this, what the code says about it. Code says you have 3 categories here when it comes to your design for structural members in pre-stress. You have uncracked system. If you like to have it uncracked, you can. Or you can have it cracked if you want it. Does it make sense? So you can have it cracked, you can have it uncracked. Or you can have it as the transition, is the class is going to be called transition. It's good, right? How can I have it to be uncracked? In this case, you keep the tensile stress at top or bottom fibers at any of the end conditions or any fibers within the concrete, you keep it within 7.5 square root of A prime C. If you do it this way, I'm going to call it uncracked member. I'm going to say, how about ASHTO and Caltrans design specifications? Some of the codes they bring to 6 square root of A prime C. But 7.5, if you remember, that was the mods of rupture. This is the one that we use when it comes to cracking stress. You guys remember this based on the ACI code? I said, okay, yeah. If you keep the stresses below, the tensile stress is below 7.5 square root of A prime C, it means the structure or the section is uncracked. And you have here full protection. You can design it to be cracked if you want to. If this is gonna be your, I mean, if you're okay with it to be cracked because you don't have any moisture content and you don't have any colorides, it's gonna be okay. You can go to 12 square root of A prime C. Shouldn't be a problem. But of course, you need to have reinforcing, right? You cannot just leave it this way. You're gonna have some reinforcing. If you like to have it like in this class T, which means transition, it's gonna be okay to be in the middle. There is no problem with this. But also recommended to have some reinforcement. It says here the pre-stressed two-way slab. If you like to have it as U, you keep the stress values, the tensile stress value to 6 square root of A prime C. So, okay, now I see here the 6 square root of A prime C. Designers usually they'd like to keep it below 6 square root of A prime C. Just to be safe, because what happens in many cases, you have a slab and next to it you have a beam. And you like to be homogeneous in your design. You'd like to be consistent, not consistent. So what do? You just keep the stresses to be 6 root of A prime C. And with that, you are matching some of the code sections in dashed. So you should be fine. Now, we need to look at the stresses. If you remember, I came here to a certain point, and then I said, maximum stress and compression is going to be 0.45 F prime C at the surface. And they say this is going to be 0.6 F prime CI at the initial pre-stress, instantaneous pre-stress. So someone here is asking and say, where'd you get these numbers from, right? Why? Why is that? What's happening? You say, okay, let me show you what's happening. Let me show you the source of this information. So it says here, this is going to be the maximum permissible, which means allowable stresses in the concrete and the reinforcing. I'd like to see where it's coming from. I guess we know what is F prime C. Strength at 28 days. Specified. F prime CI at the time of the initial pre-stress. Yeah, this is the one that we considered here to be 4,800. And we say typically we're going to be using it in 10 days. This is construction, actual projects. FPY is going to be the yield, which we say is going to be 85% of the ultimate of the pre-stressing strains or tendons. FPI is going to be the initial. This is the one that we called 189. And effectively, we say it's going to be 150. Now, I'd like to see the source of all of this information. You say, okay, here's what the code says. Depends on the location in the beam itself. This is going to be right at the pre-stressing, which means at the FPI. So they say here the stress, which means the stress here. You see the stress at the FPI when you do instantaneous check. You say maximum compression is going to be 0.6 F prime CI. You say, did I see this before? I'm going to say, yeah, it is right here. You guys see this? 0.6 F prime CI. They said this can be the maximum compression where? At the middle sections of the beam. How about this value here? 70% of F prime CI. It says at the end of simply supported beams only. So if you have a beam, you come here to the end, right? Which you're going to have the anchorage, you're going to have the big force. You say maximum compression is going to be 70% of F prime CI. In the middle, which means any other sections, is going to be 60% of F prime CI. So for me, when I did this example, we just used 0.6 F prime CI. Now we understand the reason. Because if I see here two values and I don't want to be confused in my analysis, I'm going to say, you know what? Let's just keep the 0.6 F prime CI, which is a lower. And if I can keep the compression throughout the entire beam, beginning and the end, it means I satisfy this section. So now I understand where is the 0.6. Where is this coming from? From the ACI. They say also in tension, I'm going to have here two values. 6 square root of F prime CI. This is what? This is right at the end of the simply supported. In the middle is going to be 3 square root of F prime Ci. One, the tensile stress is going to be exceeded. I need to have bonded rebars. What's the bonded rebars? The bonded rebars is going to be the conventional rebars, like number 4 and number 5. This is what you call here bonded rebars. Said, okay, this is good. I see here in the slide that I put it myself. How about the code section? I'm going to say, here's the code section. Here's the table taken from the ACI. 0.7 and 0.6. Now we know where it's coming from. It says here's going to be the concrete tensile stress limit immediately after transfer. This is why I put this immediately in a box. It says here, at the end is going to be 6. In the middle, all other locations going to be 3. Good. But this here without additional bonded reinforcement. So with that, you don't really need to add reinforcement. If you can keep the stress like this. One, the stress is going to be going above this limit. What's going to happen? You need to have reinforcing. See this? So now I understand the statement here. Where this comes from? I know that this statement here is not in the code. It doesn't say it this way. But it says, if you keep the stress within this limits, you're good. You have no problem. You don't really need to have reinforcement. It says without. So I'm going to put this in the box, without. Okay, good. How about the surface load? Yeah, surface load. What's going to happen? Compression. Let me put this back. We said, how much is this? 0.45, right? This is going to be 45% of this. Okay, 45%. Yeah. For what? For the pre-stress force, sustained load. Only for the pre-stress and sustained. When you have the pre-stress and total, which means sustained and life load, you can go all the way to 60%. Great. That was not indicated here, I understand. But you know what? If you're doing a design and you keep the stress throughout the entire beam at 45% of F prime C, you're good. You are covered with this. And then again, when you have the tension, uncrack and transition, right? And of course, you're going to have your reinforcement. So you say, okay, where is this in the code? I'm going to say it's right here at service load. Look at the service load. 45% and 60% over prime C. This is going to be pre-stress plus sustained load. What's sustained load? Like additional dead load. So in this case, I'm going to have the pre-stress force, dead load, and additional dead load if I have any. Once I add total load, it means what? I added here the life load. I can increase to 6%. And this section here, we have seen it before. But again, we have seen something similar to it. Difference between uncrack and transition. How about the crack section? I'm going to say no, we don't like to see it in pre-stress, generally speaking. But you can design for it if you'd like to. And here's going to be the limits, right? For uncrack versus crack. This is okay. The tensile stress in the pre-stressing tendons themselves, you cannot go beyond 70% of FPU. I said, I have seen this 70%. Where did I see it? Okay, let me check. And also, I have seen this 80%. I'm not sure. So 80% and 70% of FPU. Remember this. Let me take you back here quick. You'll see, yeah, we have seen it here. You remember these numbers? The 70%, 82%, they're right here. Now it makes sense. Now I know where this is coming from. It's true that this value, I put it here, but now I understand the reason why I put it here, because of the code limits. And the code limits is going to be right here. It says 70%. So, okay, good. Now I understand. How about the stress in the concrete itself? Before losses, which means immediately. You say, okay, where is this taken from? That was what? That was the ACI 318. Look at this. This is going to be the bridge design specifications. The Caltrans specifications, they have different values. And they have something here for temporary stress before losses, which means instantaneously. How much was the stress that they used when it comes to compression? 0.6 F prime C. When? Temporary. Before losses, which means immediately. But they call this F prime C. I see it. How about an area bonded reinforcing sufficient to resist? What is that? This is going to be tension. 0.24 square root of F prime C. Okay. Little bit difference, yeah, acceptable. How about here? Just continue here with Cantron's specification. 0.45 and 0.6. I guess this here matches the ACI. If you look here at 0.45 and 0.6, you can see, yeah, this is matching here the ACI. 0.45 and 0.6, yes. Same as the ACI code. How about this value here? 0.6 F prime C, compression, instantaneous. Do you know which value we have used here for the ACI? I'm gonna take you back here. Allow the stress and compression instantaneous. Anyone remembers the value that we have used? Here we go. 0.6 of what? F prime CI. Catron says just F prime C, which is here some difference between the ACI. So if you are working bridge design, you may end up with different stress values and different design limits. If you work here with the ACI, which we're going to be using, you need to stick with the ACI limits. Questions? I guess we came here to an end. Let's see you next time.